All right, hey there, welcome back to part 2 of chapter 6. And we're just going to pick up right where we left off. We were learning about quantum numbers and electronic configurations. And a really important thing to know is that the energy of an atomic orbital increases as the principal quantum number n increases. Okay, and as the principal quantum number n increases, the size of the orbital increases as well. And the electrons spend more time farther from the nucleus. So the higher the energy level, the higher the n value, that principal quantum number, the farther away you are from the nucleus. And that makes sense. If the nucleus, we learned about this in chapter 2, actually we'll use a penny instead, huh? It is this tiny little penny. We know that the entire electron cloud could be as big as a football field. And so, you know, it's far away and then farther away and then farther away, and they just build from each other in these spheres. Okay, so the attraction of the nucleus is weaker and the energy associated with the orbital is higher. So the farther we get away from it, okay, if we've got the nucleus in the center, then here it can see the nucleus, and here it can see the nucleus a little less because there's these negative spheres of electrons in here. And so each successive energy level is not only farther away, but it's being shielded from seeing the nucleus. And so the nuclear charge is the effective nuclear charge is weaker. So because of that, electrons tend to fill low energy orbitals first. And again, those low energy orbitals are the ones that are the low energy orbitals are the ones that are closest to the nucleus. All right, so this image is showing you a little bit about how that fill goes. So, oh, hang on, I'm trying to move things around my screen to see them. Okay, so as we look at this, so first of all, if we're starting here, so here's start, okay, and everything starts in 1s. Now, watch, and you can watch this order of fill at the bottom, and you can see how what I show up here is going to match this. So as we go up, we go to 2s, and then 2p, and then 3s, 3p, and now notice here's 3d over here, but here's 4s. So then we go to 4s, and then 3D. And then after 3D, we have 4P. And again, 5S is the next one as we go up our stairs, and then 4D, 5P, 6S. And now before we get into any of these, we come all the way over, and the next one on the list is 4F, 5D, 6P, 7S. And then you can keep on going, so forth and so forth. And down here, you can see this order of fill. Now, there's, it's in your textbook, and if you can use it, you can, and it's this thing with the multi-arrows. I don't like those at all, but if they help you, you should use them. But I don't like them, and the reason I don't like them is I feel like they don't, to me, it doesn't show why. It doesn't give me an idea of why I'm seeing that. When I'm trying to remember this order of fill, I use the periodic table because I'm kind of a why person and not just a what person. But again, if it helps you, you can use those, and they're in your textbook. So following that order of fill is going to give us an electron configuration for each atom. And that's going to show where the electrons in the atom are. Determine the electron configuration for an atom, we need to add the number of electrons equal to its atomic number. So if we're talking about oxygen, which is atomic number 8, it has 8 protons and 8 electrons. So we have to account for all 8 of those electrons. The procedure is called the Aufbau principle, which I guess literally in German just means to build up. And it's just you're building up. The Aufbau principle tells you how to like add into energy levels, next lowest, and so forth and so forth. All right, so this is what I mean about how, this is what I like to use. I like to use the periodic table. So let's take a look here. We start with 1s, and here's our 1s. 1s1, 1s2. Okay, and then we have 2s and 2p. Okay. Now I'm going to go ahead and change color as we go. Then I have 3s, 3p. See how that works? And then we have 4s. And then see, we fill these 3ds. And then 4p. Now you'll notice if you compare the slides to your textbook talks about exceptions for how things fill. I don't want you to show me exceptions. Sometimes, and later in this chapter, when we talk about ionization energy, I will talk about very important exceptions. However, right now, the most important thing is that you understand which orbital things are going into in a general sense. If you start trying to look for the exceptions, then you'll end up memorizing it. And I don't want you to memorize these. I want you to understand where they come from. Okay, so that's a really important thing. If I ask for something on a test and you give me the exception, then I know that you have looked it up in your textbook and just written down the answer rather than thought about it. So I am looking only for the elements as they would follow the rules. So don't give me any exceptions in this point. Use your mind to think about what they would actually be. All right, now again, after this row, next I have 5s and then 5d and 5p. This is why I say I use the periodic table. I think it's really easy to see. And then 6s. Now from 6s, we come down here and we fill 4f. And then 5d and 6p. Okay. And then last we have 7s, 5f, 6d, and then these down here, which would be 7p, except that they don't really do anything. They don't exist for long enough to actually do anything interesting. However, if they did, this is where they would be. Okay. Okay, so now let's take a look at electron configurations and orbital diagrams. Okay, so when we're looking at this, this right here is the electron configuration. All right, I don't know. Electron configuration. And this, the arrows, this is the orbital diagram. All right. Orbital diagram. Okay. And remember, I said that we'd be looking at them up. So remember, hydrogen then is 1s1. So before, if you're watching this at home, I got my periodic table here. Remember on the last slide, I just showed you where to find these. So if you don't have your periodic table sitting in front of you, I want you to pause the video and go get it. And as I'm doing this, I want you to be looking at these. Okay, so now hydrogen has 1 electron, and so it's 1s1. Helium has 2 electrons, so it has 2 electrons in that 1s shell, so 1s2. Lithium has 3 electrons, so 1s2, 2s1, and the electrons would add like this. Beryllium has 4 electrons, 1s2, 2s2, and you would show it like this. And you can just keep on going. I think my next slide, I know where my slides are. I want to make sure, so I'll do something by hand if I don't have it. Oh no, I do. Excellent. All right. All right, now let's take a look here. Hund's rule says that the lowest energy configuration for an atom with electrons within a set of degenerate orbitals is that having the maximum number of unpaired electrons. All right, so what does that mean? What that means is, so we look at nitrogen here. Now nitrogen, if you look at it, nitrogen is number 7. And you can see that it has 1s2, 2s2, and then 1, 2, 3 electrons, 2p3 in that p block. And so you fill in your 1s2, and then you fill in your 2s2, and then you come to your p block. And within your p block, you have 3 p orbitals that are all exactly the same. So imagine that this is sort of like kids in picking rooms. Okay, if you have 3 kids and 3 bedrooms, they are probably not going to choose to share. Okay, they're probably each going to choose their own one, and your electrons are sort of like that. So then when you get there, then we put them in, so 1, 2, 3, 4, 5, 6, 7. Okay, and then when we get to oxygen, and oxygen has 8 electrons, then you would count 1, 2, 3, 4. And now watch, 5, 6, 7, 8. Now that's where you start doubling up. Now, the fact that here we start doubling up, that's going to be very important later. Remember I said there were some really important exceptions when we get to ionization energy. And that one is one that I want you to remember. All right, 8 electrons. Now, fluorine has 9 electrons. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then you can see them here, 1s2, 2s2, 2p5. That 5 goes with these. Now we've got neon, 10 electrons. Now let's watch these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, now let's take a real close look at this. Do you see this 2p6 and 2p6 here? All noble gases end with a number and then p6. And that'll end up being really quite important later. Okay, and then you could keep going with this as far as you needed to. And you could just draw boxes that go with that order of fill that we saw before. All right, now let's talk about valence versus core electrons. All right, so see here we have, so valence electrons exist in the outermost shells, and core electrons happen all the way up until the most recent noble gas. Okay, so let's take a look at that. Right now, we're looking at sodium. And sodium has 11 electrons. Okay, and now let me go ahead and draw those boxes here. Okay, that's 1s, 2s, 2p, and 3s. Okay, and now I have 11 to place. So we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then we can see here, that means that would be 1s2, 2s2, 2p6, 3s1. Now, if you remember from the previous slide, this right here, this was the same as neon. So we can write these, both of them, and we would call this a full electron configuration. And this is sometimes called either an abbreviated electron configuration or a noble gas electron configuration. And so the full electron configuration gives you an image of what everything looks like. And you can see that this is what we have for core electrons. And then here we have valence electrons. And I think that the full electron configuration can be very good because what it does is it really makes it very, very clear how far out the valence electrons are. Using the abbreviated electron configuration is very useful because it tells us what our valence electrons are, but it doesn't necessarily give us a good idea of just how big our shells and subshells are. Okay, so now let's take a look at some of this for practice. Okay, write both configurations for the alkali metals, sodium and potassium. I want you to grab this and I want you to watch as I'm doing it. I am not going to be writing all of the boxes because we're looking for configurations, not orbital diagrams. So remember, the orbital diagrams are the boxes, but if I ask for an electron configuration, you don't have to do that. So let's go ahead and take a look here. First of all, we have the alkali metals, sodium and potassium. And actually, I did sodium on the previous page, so I'm not going to do that one again. Let's look at potassium. All right, potassium is K, and it is number 19, so it has 19 electrons. Okay, and I actually look at my periodic table. If you look at my periodic table right here that I'm working off of, I don't know if you can see this, but I have the numbers written on the side here. So I have a 1 written next to my hydrogen, and a 2 written next to my lithium, and a 3 written next to my sodium. And then I have a 4 written next to my potassium, and I have a 3 written next to my scandium. And not because I can't remember them, but because it keeps me from having to count. It's just about being lazy. So I look at potassium and I see that potassium is 4 rows down. So we'll say it's in the 4th row. Okay. And that's going to give me a little bit of an idea. You know, if I'm in the 4th row, then I start counting them. So first of all, my first row is 1s2, and that one's full. And then my second row is 2s2, 2p6, and that's full. Okay. And this, what I'm doing is I'm following that order of fill that I had shown you guys a few slides ago. So make sure you write that down if you're not sure. And then I'm looking at my 3rd row, and 3rd row is full, and I have 3s2 and then 3p6. And now I come down to the 4th row and I see that potassium number 19, and it's just the first element there, which means because it's the first element there that I will finally have 4s1. And you'll notice, if you remember back to the previous slide when I was doing sodium, we ended with 3s1. So an interesting thing is the alkali metals. Okay, so alkali metals will always end with a number S1. Okay. Now, if I want to make a noble, both configurations, right? So I need a noble gas configuration now. So I go back to my last P6, and I see my last P6 was argon. And then I have 4s1, and that is my noble gas, or my abbreviated electron configuration. Now I'm looking at 2 alkaline earth metals. I have magnesium and calcium. So let's take a look at magnesium. Magnesium is number 12. So it has 12 electrons, and it's in the 3rd row. Okay, so that means that my first 2 rows are full. So I have 1s2, 2s2, 2p6. Okay, and now I'm looking for that 3rd row, and I see that I have 2 elements, sodium and magnesium, in that 3rd row, which means that I have 3s2. Okay, and then I can come here and I can say, okay, well, I'll come right under my 2p6. And if I go back, I see that my 2p6 is neon and 3s2. Okay, now let's take a look here at our calcium. All right, so calcium is number 20. Okay, so we have 20 electrons. Okay, and it's in row 4. So that means that my first 3 rows are full. Okay, so I know, see here I had 4th row and it was number 19. So I know that 20 electrons is going to look a lot like 19 electrons. So that means I know that I'll have 1s2, 2s2, 2p6, 3s2, 3p6. And now I have the 2 elements, potassium and calcium, in this row. So I am at 4s2. Okay, and then I can come down here and I can say, okay, well, I come to my last P6, because remember, P6 is how noble gases always end. And I see that my P6 is argon, and then I have 4s2. So now if you look here, you have a 3s2 and a 4s2. So you know that alkaline earth metals always end with S2, something S2. That's how they always end. And these groups, especially these named groups, they're all very, they have a lot of the same properties. They're very similar. And understanding that the reason that they're so similar actually has to do with this. This is what we're doing right now, is explaining why, for example, this is explaining why. So look at this. See how all alkali metals end with S1? That's why they all end up with a 1+ charge. And these alkaline earth metals all end with an S2. That's why they all have a 2+ charge. So this is why you see those charge trends. Okay, now let's take a look at our halogens. We've got fluorine and chlorine. Okay, so fluorine is number 9. It has 9 electrons, okay, and it is in our 2nd row. So that means only the 1st row is filled, and the 1st row is just 1s2. And then we have 2s2. It's not an alkali metal or an alkaline earth metal. And then we look at our p block, 1, 2, 3, 4, 5. Okay, so we know we're at 2p5. Now this one's a little trickier for that abbreviated configuration, that noble gas configuration. We don't have a P6. What you got to remember is that helium is our 2s2. So when I said that all noble gases end with a P6, except helium, okay? Remember, and I'll even put that over here. I'm not sure where. Here, let's, I'll put it right down the bottom. Helium is the exception to that. And helium is that 1s2, 2s2. So it's different from all the other noble gases. Okay, so this is helium, and then we would say 2p5. Now let's look at chlorine. Okay, chlorine is down a row, and it has 17 electrons, and it's in the 3rd row. And because it's in the 3rd row, we know that the first 2 rows are full. So that means 1s2, 2s2, 2p6. Okay. And then we come down to our 3rd row, and it's not an S block. So we have that 3s2. And then we have 5 electrons in our p block. So 3p5. Okay. So now you can see that we come to our last P6 here, okay, and we can see neon, and then we have 3s2, 3p5. So you can see here that we always end our halogens. Our halogens always end with a P5. And see how here you have 7 valence electrons. It only needs 1 more to get from chlorine only needs one more to get to argon. So that is why they tend to form this 1- charge. Okay. Okay, now let's take a look at a few more. And again, so we're showing electron configurations for scandium, cobalt, and mercury. Okay, now this is where there are some exceptions to this rule. And here I want you to just work on the Aufbau principle, the building up principle. It's what I want to be focusing on here. So scandium, we need to find it. Scandium is Sc. Okay, and it is 21 electrons, and it's in the 4th row, but it's D block. Okay, these are all going to be D block. So we'll get there. So because it's in the 4th row, we know we can add everything through our 3rd row right away. 1s2, 2s2, 2p6, that's 2nd row. Now 3rd row is 3s2, 3p6, that's 3rd row, and we're in the 4th row. And so we look at where scandium is, and we see that we have 4s2, that's potassium and calcium, and then we have 3d1, okay? And that's because that 4s orbital is lower in energy than 3d orbitals, and that's why it's filled first. Okay, and now if we come here, we can write down, we can come back to your last P6 and we'll write our noble gas configuration there. 3p6 brings us to argon, and then 4s2, 3d1. Okay, now let's take a look at cobalt. CO, and we know that cobalt is one of our electrons, is one of our elements that can form multiple cations, right? You can have cobalt 2 or cobalt 3. And the reason for that is that things are kind of, wishy-washy within our d orbitals. And so we kind of have to take that into account a little bit when we're coming up with charges. So cobalt has 27 electrons. And it's also in our 4th row, but it's a transition element, which means it's going to be in the D block, and we're going to have this going down. So now, once we know we're in the 4th row, we know that we have all this that looks like argon. So I can do that again, 1st row, 2nd row, 3rd row. All right, now let's pay attention to what we're doing. So now we have 4s2, because we know it's not S block, it's cobalt. And then we count from scandium. 1, 2, 3, 4, 5, 6, 7. 3d7. Okay. And just like before, it'll have a similar where we start with argon and 4s2, 3d7. Okay. Before I go on, let me do just a quick little review over here. Say a review. So S orbital can have 2 electrons. P orbitals can have up to 6 electrons. D orbitals can have up to 10 electrons. And F orbitals can have up to 14 electrons. And actually, I'm going to turn these into little arrows so that you know that they don't have to have this many, but they can have this many. Okay? All right, now let's come over here. Now we have mercury, Hg. Mercury is quite a ways down there. It is number 80. It has 80 electrons. And actually, I'm going to take that number sign out. 80 electrons. Oh my goodness. And it's in row 6. 6th row. Okay, so 1st row, 1s2. 2nd row, 2s2, 2p6. Okay, 3rd row, 3s2, 3p6. Okay, 4th row, 4s2, 3d10, 4p6. Okay, 5th row, 5s2, 4d10, 5p6. And now we're into our 6th row. And actually I was thinking I should isolate these a little bit. So here you've got 1st row, 2nd row, 3rd row, 4th row, okay, and 5th row. Okay, hopefully you guys are, and in the next one, we're going to do a really, really big one. Okay. All right. Now here we are in our 6th row, and that starts with 6s2. Okay. And then mercury is the very last one in there, but I see, oh, I can't forget 57 to 70 are our lanthanides. Oh my goodness. So instead of 6s2, that drops all the way down to 4f14. And then I have 10 in my D block, and I'll have 3d10. All right. And now I can come down here and I can say, all right, my noble gas, if I go back to 5p, that would be xenon. And then I could write 6s2, 4f14, and 3d10. Okay, hopefully this is sort of starting to make some sense. All right, now, big one here. We are going to do promethium. All right, promethium, I should have found it first. Huh. All right, where are we at with promethium? I'm looking, you look on your periodic table too. There it is. Oh, this isn't nearly as high up there as I thought it was. Well, let's go with something really crazy. Instead of promethium, because promethium isn't that much different than mercury, let's go all the way to the top and let's do curium. Curium, CM, is number 96. So it is 96 electrons for the brief period of time that it is stable. And it is in row 7. Wow. Okay, we haven't had a row 7 yet. Okay, so let's take a look here. So I'm going to go ahead and do what I've done before. And here's 1st row, 2nd row. And then, hang on, this ended up not working very well. There we go. Okay. So 1st row, 2nd row, 3rd row, 4th row, 5th row. Oh, that should be a 6. 6th row. Okay. And then I know that I've got my 7th row kind of hanging off here. All right. So 1st row is 1s2, 2nd row, 2s2, 2p6, 3rd row, 3s2, 3p6, 4th row, 4s2, 3d10, 4p6, 5th row, 5s2, 4d10, and 5p6, and 6th row, 6s2, now remember this from the last one, 4f14, okay, 5d10, and 6p6. There we go. All right, now here we are in our 7th row. And in 7th row, I look again to figure out where my curium is, so don't forget. Okay, 7th row is going to start with 7s2, and there's curium, number 96 in my actinoids or actinides. Whether they're called actinides or actinoids, it's kind of like English spelling versus American English spelling. All right, now I have 1, 2, 3, 4, 5, 6, 7, 8. So that becomes 5f8. Okay, and then I could say, well, here, my row 6, I end with a P6, and the P6 then is going to be radon, and I'm just looking backwards at the previous noble gas, 7s2, 5f8. Okay, a lot to that one. All right, let me see where I'm at. There we are. Okay. Now, okay, so electron configuration. Recall that ions are formed when atoms gain or lose electrons. So we have cations, and a cation is a positively charged ion, and it's formed when one or more electrons are removed from an atom. So we've got examples here are sodium plus and strontium 2 plus. Okay, now I showed sodium once before at it's number 11. Oh, hang on. It has 11 electrons. Okay, and I'm just going to show this quickly because I've already shown it once before or twice. 1s2, 2s2, 2p6, and 3s1. Now, when sodium loses 1 electron to become sodium plus, now it has 10 electrons. And it just loses this last one, 1s2, 2s2, 2p6. So you could say that this is just like neon and 3s1. Oh, my allergies are killing me this summer. It's crazy. Everybody's going to watch me sneeze for the next 10 years. All right. And in this one, you could say that this is just neon, or see, you've got this 1s2, or you could say that it's helium with a 2s2, 2p6. And honestly, I've taught out of enough textbooks that I've seen both of these. Okay. And so the ion, there you have the ion versus the atom. Okay, now let's look at strontium 2 plus. So let's first look at strontium SR, and it's number 38. I keep doing that number sign. I don't want to do that. I want to say 38 electrons. Okay, and it's in row 5. Okay, now what I'm going to do though is right now I'm just going to go ahead and show this instead of just that. Now we get to strontium 2 plus, we'll have 36 electrons, and strontium 2 plus will look exactly like krypton. Okay, because krypton has 36 electrons. Okay, so you could say then, I guess, that strontium is krypton. Or you could say that it's argon with a 4s2, 3d10, and a 4p6. Sometimes it's easier to start with this. And then to show the whole electron configuration, actually, I'll come down here. Then you would say 1s2, 2s2, 2p6, 3s2, 3p6, and that's where we get to argon. And then we have 4s2, 3d10, and 4p6. Okay. Now let's look at our anions. An anion, remember, is negatively charged and it has gained 1 electron. So first of all, I showed chlorine before. Chlorine has 17 electrons. Okay, and we showed that once before, but chloride has 18 electrons. And again, because I think it makes it a little easier to see, well, chloride looks just like argon, and that helps us kind of identify where we are. Or we could also say that it looks like neon plus everything you need to make argon, 3s2, 3p6. Okay. Or you could say the whole thing, 1s2, 2s2, 2p6, 3s2, 3p6. And all of these three things mean the chloride ion. Okay, they all mean the chloride ion. And what we're doing is we're just showing it in different amounts of detail. All right, now here we have selenium. Selenium has 34 electrons. But Se2 minus, that's selenide, if you remember. Selenide has gained 2, so selenide has 36 electrons. So those 36 electrons, well, now it looks just like krypton. And krypton looks just like argon plus 4s2, 3d10, 4p6. And the whole selenide together looks like everything before that. And I'm not going to add those in. Okay. So just to show the difference here, selenium would be argon. And then 4s2, 3d10, 4p4. Okay. So here you can see that difference when you're adding and subtracting electrons. All right, so now let's take a look at some periodic trends. We will do more of that when you guys come to Zoom or to class, okay? And here we have our electron, oh, I'm not even sure where I am, there I am. Okay, periodic trends. So there's 3 periodic trends that are real key. Okay, one of them is the size or the radius of atoms and ions. A lot of times you'll call this atomic radii. And it's basically how big you are. So big versus small, we'll say. Okay, next we have ionization energies. And ionization energies is how much does it cost? Oops, does it cost in energy to remove an electron? And last, we have these electron affinities. And electron affinity is how easy is it? Oh, is it to add an electron? And I'm actually not going to look at electron affinity here because I find that there are so many exceptions to the electron affinity rule that it almost doesn't make sense. Next chapter, in chapter 7, we will actually cover something that makes way more sense than electron affinity, and that's electronegativity. And we'll learn about that instead because, and I think that that makes, it's almost the same thing, but it means so much more. All right, the covalent radius is defined as 1/2 the distance between the nuclei of 2 identical atoms, and they are joined by a covalent bond. What? Okay, the covalent radius and the atomic radius are basically the same thing. However, the atomic radius is really, really hard to measure because we don't have anything, we don't have another nucleus to measure it against. So it's a lot easier to find the covalent radius when we're doing that. So an example of covalent radius, let's say that we're looking at oxygen gas, okay? And oxygen gas, we have our 2 oxygen atoms there, okay? And here we've got our little, our nuclei, and here we've got our nuclei in the center, okay? And the covalent radius, well, here's our distance, okay? This is the distance between the 2, and the covalent radius is half this. Okay, so the distance between the 2 nuclei is this, the covalent radius is half this, and you can see, well, there we go. Okay, it's another way of looking at atomic radii. The covalent radii is usually a little bit smaller than an atomic radii, but sometimes this is easier to see. All right, now as we go down the periodic table, the principal quantum number increases. So we know that as we go down a periodic table, we have n is equal to 1, n is equal to 2, n is equal to 3, and so on and so forth. Okay, so the electrons that are added to each one get farther and farther away. So it totally makes sense that as we're adding these like this, our atomic radius or our size of our atom increases as we go down the periodic table. Okay, now as we go across the periodic table, we're still in the same n value, but you know what we're doing? We're adding protons. Okay, so over here, I'll say size goes from smallest to largest as we go down. Now, as we go across the table like this, we're adding protons, and those protons are positively charged, but we're still in the same thing. So here's our shell, right? But we're adding more positive charges, and what those more positive charges do is they pull the electrons tighter and tighter and tighter and tighter and tighter. So this is going to seem super weird, but we're larger on this side of the periodic table and smaller on this side of the periodic table, because the protons that are being added into the same energy level are pulling on those electrons even harder. Okay. So what that basically means is we're talking about something called ZF. So that's Z effective, or the nuclear charge, the effective nuclear charge. And what's happening is that the effective nuclear charge is talking about how much of the protons that the electrons can see. Okay, and we're not going to get too much into that, but it's taking into account electron repulsions. But that's one of the reasons that we see Z effective increasing as we move across a period. And as Z effective increases, we squeeze those in tighter, which changes our atomic radius. All right, now this is such a cool graphic, trends for atomic radii. Okay, now you can see that these are amazing. There's very, very few exceptions, and these are kind of hard to see here. So all right, so these tiny ones here, this is the 7A, this tiny one here that they're showing, this is hydrogen. And this one here is helium. Okay, 37 and 31. So even just going across, and when we complete that, that shell, we pull that helium in smaller. Now look here, lithium is an atomic radii of 152 picometers, all the way down to neon at 71 picometers, and you can just watch it go across. I don't know the transition elements in there, because as you can see, the transition elements are kind of weird here in the middle. But if you don't look at the weird transition elements right here, but even the transition elements make this neat little swoop. Okay, but even here we go from 227 down to 112 in our potassium row, and there's no exceptions. You have to come all the way down here to tin, antimony, and tellurium to see exceptions where we get smaller and then bigger and then smaller again in here as well. So until you get there, though, if you look at large things, 248 to 131. So that increasing nuclear pull is pulling so tightly. Okay, it also means that our periodic table, the largest are here and the smallest are up here. And you can actually draw a line that just goes up like that between largest and smallest. Okay. Right now, ionic radius is a little bit different. So in an ionic radius, as we remove electrons, so a cation is removing electrons. So cation, remember, we're losing electrons in a cation. We're losing electrons so that we look like something with fewer electrons and fewer protons. Okay, so a cation is always smaller than the atom from which it was derived. But in an anion, we're adding electrons. Sometimes the annotations are weird. All right, sorry, adding electrons. An anion is always larger than the atom is from which it was derived. And that's because you're adding more electrons, but you're not adding more protons, which makes it this big thing. Okay, that leads us to an isoelectronic series. So if you're looking in the extra help for this chapter, if you need some extra help with the isoelectronic series, look in the chapter 8 extra help folder, because in previous textbooks, this was actually treated in the following chapter instead. Sorry, chapter 7, everything's different here. Just know that it's there. But examples of isoelectronic series Okay, so an isoelectronic series has the same electron configurations. Okay, so well, what does that mean? First of all, if we look at our periodic table, we can see that neon has 10 electrons. Fluorine, oxygen, fluoride, oxide, and nitride also have 10 electrons. Sodium loses one, so it has 10 electrons. Magnesium has 10 electrons, and aluminum has 10 electrons. You see where this is going, right? Okay, so they all have the same number of electrons, but let's take a look at what happens to the protons. Nitrogen is number 7, so we have 7 protons, and then 8 protons, and 9 protons, 10 protons, 11 protons, 12, and 13 protons. Now, what do you think? When you have more protons pulling on the same number of electrons, this is totally like tug of war, right? Okay, if you take 10 people and 13 people and they're all the same size, what do you think you're going to get? Of course, the 10 is going to lose. Okay, so that means that the more protons we have pulling on them, whenever you have an isoelectronic series, the aluminum ion is the smallest because you have all these protons pulling those electrons really tight, and the nitride is the largest. And that's for our ionic radii. All right, now let's take a look at this one. Argon. All right, you know what I'm going to do? I'm going to make this more like a chart. Electrons and protons like this. All right, now let's take a look at this one. Argon is number 18, so it has 18 electrons, and they all have 18 electrons. Look at that. 18, 18, 18, 18, 18, and 18. Hurrah. Okay. And then, but now let's take a look. Phosphorus is number 15. That means it has 15 protons. Sulfide has 16. Chloride has 17. Argon has 18 because it's neutral. Potassium has lost, so it's 19, 20, and scandium 21. Okay. So again, same thing. More protons pulling on the same electrons. This is going to be the smallest, and this one is going to be the largest. Now, this is the other thing that's really interesting. The isoelectronic series, all of these ions, all of these anions, all of these cations, and neon all have this electron configuration. Okay, now we're with argon. Here we see a noble gas or an abbreviated electron configuration, and this noble gas or this abbreviated electron configuration goes with all of these anions, argon, and all of these cations as well. All right. Okay, ionization energy. Said we were going to get to that. Ionization energy is, so this talks about all the real stuff going on here. Ionization energy is the energy cost to remove an electron. So it makes sense when you're just looking at here that it's really easy to take an electron off of sodium because it's an alkali metal and we know that. But then on the other side, it would be really hard to take an electron off of chlorine. Chlorine doesn't want to lose electrons, it wants to gain electrons. So if you draw out your periodic table, as you go down the periodic table, your ionization energy decreases. Okay, and why is that? Well, it decreases for the same reason that we saw our atomic radius increasing. It decreases because our electrons are getting farther and farther away from the nucleus. Because they're getting farther and farther away from the nucleus, it makes it easier to remove one. Now, as we go across the periodic table, it increases. Okay, and the reason it increases is that as we get closer, as we add those protons and more and more and more protons, it's hanging on to the electrons more and more and more tightly until we reach that noble gas configuration with stability. Okay, so as it increases means it's harder to remove an electron. Okay, and decreases means that it's easier to remove an electron. And the easiest electron to remove is down here, and the hardest electron to remove is up here with fluorine. All right, now this has some really, really important and interesting looking exceptions. And I remember one time a student asked me in class, well, are you going to trick us? Are you going to give us one of those exceptions? It's not a trick if I tell you I'm going to do it. Okay. And it's not a trick because it's not an exception. It's part of the rule. So it's an exception to the trend, but it's not an exception to the rule, just the trend. Sort of like when you're learning spelling and you learn I before E, that's the rule, except after C, also part of the rule. And in words that say A, like neighbor and way, also part of the rule. This is just like that. These exceptions are in here, but they're part of the rule because they're really, really interesting and important. All right, so let's take a look at some of these exceptions. Okay, so come down here. You see how we have lithium? Now you would expect it to go up. As we go across the chart, we said it would go up. So you would expect an increase like this. But look, here you have lithium up to beryllium, down to boron, up to carbon, nitrogen, down to oxygen, up to fluorine, neon. Interesting. Well, now we take a big jump down, and there we have sodium, and then up to magnesium. And look, how weird. Down to aluminum, up to silicon, up to phosphorus, down to sulfur. Weird. So the interesting thing is these jumps are happening in the exact same places. Okay, so here we go, 520, 900, down to 800. Okay, 1090, 1400, down to 1310. Okay, now let's take a look here. We have 490, 730, down to 580, 780, 1060, down to 1000. And you can see those jumps in the same places as well. Don't look at these are weird. Okay, so let's not look at our transition elements because those are different. But look, we have 590 down to 580, 780, 960, down to 950. All right, so you see these in the same place every single time. The question is why? I have an answer for that. All right, now let's take a look at why. All of our P block elements, look, okay, this is for every single P and S. So what happens here is our S block fills up, down. And now look, now we have one that comes over here, and it's the first one here. And this green one here is like boron, aluminum, gallium. See how there's just one here? Okay. Well, it's easier to remove that one than this full shell. Okay, because here we are up in another energy level. This first one here has a higher energy level, okay, than our S block by a lot. Even when we don't have anything in between, there's a big jump there. So that makes that one easier to remove, okay? And then we would add, say, carbon, nitrogen. Now look what happens with the next one. Okay, here, look. There's oxygen, sulfur, selenium. Well, this one is a little easier to take off than this one because it had to double up. It doesn't want to be doubled up, doesn't want to be sharing, so it's easier to take it off. Okay, so here we see that they're easier to remove because there's that big jump. So it's easier to take them out because it's up higher and it took more to put it up there in the first place. And then here we see a little bit of a decrease in ionization energy because it's easier to take out the electron that had to double up first from the other ones, and then it goes up from there. All right, That is the end of the slides, the lecture part for this. Come to either Zoom or class, and we will practice these there. I look forward to seeing you all. Let me know if you need any help.